Hello, everyone, and welcome back to your channel of Math and Engineering Made Easy. You can see a circle, of course. Didn't want to waste your time. This is Mohr's circle, okay? So we are going to use Mohr's circle to look at stresses inside a material, okay? So Mohr's circle. You know that when we design an element, in the beginning, we use engineering statics to find all the forces and torques that are applied to my element, maybe a beam, a column, a machine part. And then in the second course of strength of material or uh, in strength of materials, we are going to look at what type of stresses do these forces make to the body. And then we are going to say, okay, so what materials can I use and what shape of an element should I use to minimize these stresses and maximize my performance, right? So in that step, we assume here we already found the two types of stresses that act on the body, which are the normal stress that can come from direct tension or compression or from bending moments, or shear stresses that can come from direct shear or from torsion. Okay, so every element, if I take a piece of element from a body, based on its location, I can find the normal stresses that I will draw the Mohr circle and use the x-axis of it as my sigma, or the normal stress. So the normal stress would be calculated here. And the shear stress would be, so to speak, the y. I don't know the location because the location depends on where the zero is. But I am going to assume, just for simplicity, that bottom is positive and top is negative for the shear. Notice for the shear, there is no difference. The material doesn't feel anything different if you apply a positive shear or a negative shear, right? It's just you are trying to split it into two like that or like that. It's the same thing. However, for the normal, of course, it's either tension or compression. So depending on whether the material is brittle or ductile, it makes a big difference. However, we are going to say here that we are going to use, as I said, the horizontal as sigma and the vertical as tau. And then 2 points on the circle would represent the state of stress of my part. So if here the x is here, the y would be opposite to it. If the x is there, the y would be opposite to it, and so on and so forth. Meaning, in real life, the x and the y are normal to each other, perpendicular to each other, or orthogonal. However, on Mohr circles, they make an angle of 180. If this is the x, the opposite side would be the y, and the angle between them is 180, which tells you that the angles in Mohr circle are twice their actual value in real life. So this is important to understand. And just for simplicity, so that the calculation would be easy, as I said, we are going to assume bottom is negative and top is positive for the shear. In the statics course, we learned that moments that are trying to rotate counterclockwise are considered positive, so these would be down. And if they are turning clockwise, that's negative, meaning it would be upwards. Now let's take a couple of examples. So let's say in the first example, I have an element inside the part that is subject to normal stress, and maybe we can, well, let's make them both positive for now. So let's say this is 40 megapascal, for example, and this is 100 megapascal. And let's say this is 40 The shear is 40 megapascal also going like that. And if these are rotating clockwise, so on the other face, they should be rotating counterclockwise to counter their effect, and all of them are 40 megapascal. So the x is 40, the y is 100. So the y would be to the right, the x would be to the left, okay? Now on the x, which is to the left, the rotation is clockwise, so it's negative. Negative meaning up. So my point would be to the left of the center and up, somewhere here. I don't need to draw it to scale, by the way. Of course, it's nice, but you don't have to. Okay, it's just the general shape would be something like that. So that is the x, stress at x. Sigma x is 40, and the shear is negative 40. Notice we said negative is up. On the right-hand side, I have 100. That's the y. It's 140. So what are the coordinates of this point? Anybody? If you say 70, you would be right. How do I find? You can apply the midpoint formula, right? So the coordinates of x would be 40 plus 100 over 2 is 70. And negative 40 plus 40 over 2 is 0. So that point is 70 and 0. 70 is very important. You will see why later. Now, we want to know, notice that this point has 0 shear, and this point has 0 shear. But because that's a circle, when you get 0 shear, you get the maximum normal stress and the minimum normal stress on that line. So there is a plane where there is no shear acting on it. It's just normal. All the shear is transformed into normal. I want to know what is the value here, what and 0, and what and 0. We call these the principal axes. We are going to refer to the top one as sigma 1 and the bottom one as sigma 2. Always the bigger is 1. And we call these the principal stresses, the maximum possible normal stress that act on a body. Okay? So this is a circle, and I know the coordinates of the center. If you can give me the radius, I can add it to the 70 to get sigma 1, subtract it from the 70 to get sigma 2. And in fact, that radius is also going to be the maximum shear that happens and occurs in on my element. The question is, how do I find the radius? Well, there are 2 ways, and both of them are equivalent. The first way is to apply the distance formula, right? So I can say, if I call this point, yeah, it's called y. So I can say the radius, which is OY, equals the square root x100 minus x70 quantity square plus the y, which is 40, minus 0 square equals the square root of 30 square plus 40 square equals 50 megapascal. Or you can drop a line perpendicular. It's the same thing I said, right? If you drop a line perpendicular here, that coordinate would be 100 and 0. So that distance is 30, and that distance is 40. And Pythagorean, or the Pythagorean theorem says the hypotenuse square is 30 square plus 40 square under the radical. We know 3, 4, 5, so 30, 40, 50. And that automatically becomes the maximum shear stress, tau max, that occurs here and there, top and bottom. Notice that this point would be the 70 here stays the same, 70 and 50, 70 or 70 and negative 50, 70 and 50, since we said bottom is positive for the shear. Also, if I add 50 to that, so sigma 1 becomes the 70 that is the coordinate of the center plus the radius equals 120 megapascal, and sigma 2 becomes 70 minus 50 equals 20 megapascal. That's how easy it is to find the maximum and minimum normal stresses that can ever occur during these stresses and the maximum shear stress. Notice that the maximum shear stress has normal stress with it, the 70. But the normal, maximum and minimum normal stress don't have any shear along with it. And they are 45 degrees apart. Notice it's 90 degrees in Mohr circle. And we said in Mohr circle, we get twice the angle. So if I call this angle twice theta, I can calculate theta and say theta equals tangent to theta is 4 over 3, right? Or sine 2 theta is 4 over 5. Or cosine 2 theta is 3 over 5. It doesn't matter. You don't have to use tan. But it's just because they are given to me from the beginning, I use them. But since you calculated the radius, you can use sine, cosine, or tan. I don't care. So it's 1/2 arctan or a tan. So mathematicians don't hate me. Instead of they don't like it to say inverse tan. So arctan, okay, I'm sorry. And you calculate that, so you can say 1/2 arc, I'm sorry, 1/2, I clicked the alpha instead. Arctan of 4/3 equals 26.6 or 56, 26.56 degrees. But in the Mohr circle, that would be 53.1 roughly. 53.13, so 53.1 degrees. Usually they ask you to draw the principal axes, this axis. Notice this, which are two lines perpendicular to each other, x and y, I'm sorry, x and y, is this. So in order to get to the principal axis, I have to rotate 2656 counterclockwise. Okay, so if this is my x and y, in order to plot them, okay, here is my x and y. This is what I have, right? It says 40, 100, and 40. If I rotate 26.56 or 26.6, here is 20, roughly here. So if I rotate like that, I go to the principal axis. And I'm going to draw my part like that. Notice the x was here. It became down at 20 and 0. So the x is 20 tension, 20, 20. And the y has become 120 instead of 100. So it became 120. Notice you have to be careful which face is which face. Also, the x was here. So when I rotated counterclockwise, yeah, I'm sorry. After that, so this angle here is 26.56. So now this line is represented by that plane. In order to go to the shear, you have to rotate 90 degrees here or 45 degrees from this. So you have to say, okay, if I take another 45 degrees here, So if I'm going to rotate another 45 degrees, meaning 71.56 from that, I will go to this face, right? I rotate it clockwise, counterclockwise, and another counterclockwise. In fact, I can rotate clockwise from here. So I can go down 45 degrees and I will get a line like that. But you have to be careful which one you are going to use. If I rotate counterclockwise and another counterclockwise, the Y becomes this point, which has 70 and negative 50. So the Y would be 70 and negative 50, meaning it's rotating clockwise. Notice here it was rotating counterclockwise. Here it became rotating clockwise. 50. And then another 50 here. And also 70, of course. 70 megapascal. So this is the plane of maximum shear, or the normal to it is also plane of shear, but these arrows would reverse. And these are the principal axes, and the maximum normal is 120, the minimum normal is 20, both are tensile. So this part is not subject to compression at all. And the maximum shear is 50. Okay, and that's basically how we draw it. Let's take another example where here's another circle. So I'm going to draw, just to get you to know how to do that. And this is the sigma. I want to tell you something. Sometimes in the problem, they tell you, okay, here is the current face or the current element. What would be the stresses if I rotate, say, for example, 60 degrees clockwise, meaning 120 in this, on this circle? If you have the angles, you can easily find the coordinates and find the stresses. You see what I'm saying? Meaning, if I want to rotate 60 degrees counterclockwise, meaning 120, I will go to 173.1, and I will get something like that, where this angle is 173, meaning this angle would be 6.9 degrees. If I know this is 50, we said it's 50, yes, 50. 50 cosine 699 would give me that. So I'm going to subtract it from 70 to get the normal, and then multiply it by sine 699 to get the shear. So it's really very easy. All what you have to do is to double the angle they give you, and then the rest are simple trig, like sine and cosine. It's very easy. I'm not going to waste your time on that. Okay, let's take another example. And here let's assume that x is negative. So x is compression and y is tension. Let's get some values here. So I say, I think I had an example. I just want to make easy numbers. 100 megapascal, compression on the x, and 20 on the y. So that would be 120, meaning 6. Okay, so let's make that 80 then. Let's make that 80 pascal. The compression, the shear, 80. Of course, all of them megapascal. Suppose this is the scenario. So how do I plot that here? Again, as I said, the x is compression, so the x is to the left, somewhere here. And the shear on it is counterclockwise, meaning positive. Positive is down, remember. So I will have a point somewhere here to the left and down. Where exactly, I don't know, and I don't care. I'm simply going to put a point here and say negative 100 and positive 80. Notice positive is down. And on the other side, because they are 90 degrees apart, meaning on Mohr circle is 180 degrees, it's a straight line, I get 20 and negative 80. So the coordinates of the center O are easy. I average the X. This would be 0, right? The Y would be 0 because I am on the sigma. But what is the X? Negative 100 plus 20 is negative 80 divided by 2 is negative 40. Okay, so now to find the radius, I can drop a line perpendicular from here to find a right triangle and use Pythagorean theorem. This is 80. And if this x-axis is negative 40 and this is positive 20, they are 60 apart. So this is 60. So R here is 100, right? 60, 80, 100. Or you simply use Pythagorean theorem and say R equals the square root of 60 square plus 80 square equals the root of 3600 plus 6400 equals the square root of 100,000. I'm sorry, of 3600 and 6400. So 10,000, which is 100 megapascal. That's tau max. Meaning right away, you see, it doesn't take me any time to find out this. This would be negative 40 and negative 100. And this would be negative 40 and positive 100 megapascal. Maximum shear. And now to find sigma 1, I say this is negative 40, but then I go to the right a distance of 100 and get 60 megapascal. That's sigma 1, the highest. This is 100, I'm sorry, 60 and 0. Sigma 2 would be negative 40 minus 100 equals negative 140 megapascal. Negative 140 and 0. Found everything except the angle. I found the normal, the principal stress is 60 tension, 140 compression. Maximum shear is 100. And this is 2 theta. Oh my God, it's exactly, I should have changed the numbers. But 2 theta equals arctan of 80 over 60, which is again 4/3. So it's 26.56, right? 26. It's the same, but this time I have to rotate clockwise to reach the principal stresses, not counterclockwise, okay? So in order to draw that, I'm sorry guys, I used the same ratio, 4:3. I could have made that 3 and this 4. So at least the angle would have been the complement of that. So if this is the case, we have here. Then in order to get to the principal axis, I have to rotate an angle of 2656. That's what we are going to do. We're going to rotate from here. Let's put this on the line. 26, and I have somewhere here. So these are the principal, one of the principal axes. Okay, so notice that was the X, right? So when I rotated clockwise, the X, so again, let me say this is the X. I'm sorry, this is the X, this is the Y. So when I rotate the negative 100, the negative 100 became negative 140. And the positive 20 became positive 60. Okay, and there is no shear whatsoever. Now, in order to find the maximum shear, I can either go another 45 degrees or 45 degrees in that direction. It doesn't matter. So if I go 45 degrees in this direction, meaning 90 degrees on Mohr circle, 45 degrees from here. So 45 minus that is 1843. So if I take 1843 above that, oops, somewhere here, that would be the top point, not the bottom point. The only difference is that the shear, is it positive or negative? So if I make, so I can take 45 degrees from here and make that 7156. However, if I decided to rotate in that direction, the y becomes the face that has negative shear, meaning going clockwise, and the x is positive or counterclockwise. And all of them, they have 100 for the shear and 40 compression on both faces. Oh my, blades are horrible. 40 compression. And that's how you do it. So no memorization. You will see, of course, they tell you if I want to rotate from here to here, I say sigma x bar equals sigma x plus sigma y over 2 plus sigma x minus sigma y over 2 cosine 2 theta plus tau xy sine 2 theta. And if you want to find the tau, it's negative. Oh my God. Why would you memorize? It's much easier to see it on Mohr circle, right? How to rotate clockwise or counterclockwise. You can easily, using very simple trick, find the angles, find the radius, find the coordinates of any point on the circle. It's very easy. Notice, as I said, I could have rotated 45 degrees and came to this. So the y would have been having positive shear. So these would reverse. So if I rotate this 45 degrees and another 45 degrees, meaning I make it perpendicular to this line, all what will happen is that these arrows would reverse. On the y, they would go counterclockwise. On the x, they would go clockwise, but the negative 40 would stay the same. It doesn't matter. Okay, I hope this wasn't that bad. And as usual, if you have any questions, please don't hesitate to leave me a line in the comment section. I'll get back to you as soon as I can. Thank you very much and hope to see you soon.